Hi, Wei-ju here. How are you guys doing? As a backer of the original Kickstarter project, I received this Spectrum Next a few months ago, and it's a really well-made computer. I started fiddling a little bit with it and recently decided that I wanted to start delving more into programming this fun little machine. So I grew up in Germany, and I did not own a Sinclair ZX Spectrum as a child. I had a Commodore 64 and of course the Amiga, and I programmed those in BASIC and assembly language, and I also did graphics, sound, and play games and everything that people did back then with a computer. But I always admired the case design of the Sinclair machines. Technically, those were rather simple and quirky, but that makes them actually rather appealing and charming to me. So after my home computer-filled youth, I found work as a software developer. And even after all those years, I think that programming classic computer systems is still a lot of fun. It just feels like they have more personality than current systems. Compared to current systems, they might look rather limited, but the nice thing is that you can look at one of those systems and get a really good understanding of it, which is way more difficult when you look at a modern system. And thanks to the web, technical information is way easier to obtain than back in the day. Okay, that was a little bit how I got into my retro computing hobby. Now let's get started programming the ZX Spectrum Next. In general, I want my programs to work on both the original Spectrum machines as well as the Spectrum Next if possible. And the nice thing is that the Spectrum Next compatibility allows us to make this happen. Since one of my projects is writing a compiler, I decided to look into some of the important file formats that are used on the Spectrum. One very simple but central format is the tab format, which emulates how data for the ZX Spectrum is stored on cassette tapes. On the original ZX Spectrum, programs and data are often stored on these kind of tapes, and you can still connect a tape recorder to the Spectrum Next if you want. A tab file is simply stored as a series of blocks, where a block consists of a 2-byte word in little endian format, followed by that number of bytes of data. This representation is so simple that it makes it very easy to concatenate multiple tab files into a larger one, or to split a tab file that consists of multiple blocks into its individual blocks. To merge tab files, we can use a simple standard concatenation command such as cat to join multiple tab files into a single larger one consisting of the original files without loss of information. We can reverse this process by using a tool that can read the block information and split the larger file into its individual components again. Now, if that would be everything to say about tab files, we would be done by now. But of course, this structure does not contain any type of semantics. Therefore, the ZX Spectrum has a secondary file structure embedded within the tab block organization, which involves headers and block data. In a tab file, there are typically two types of blocks. First, the header block that acts as a descriptor for the block that immediately follows, which contains the actual data. Both block types have in common that the first byte is a flag and the last byte is a checksum. The value of the flag byte of a tab block indicates whether the block is a header or a data block. It is either 0 for a header or 255 for a data block. Let's take a closer look at the header block. As I mentioned, the flag byte here is always 0. The checksum is computed by combining the 18 bytes above the checksum using the XOR operation. The block type identifies the type of data that is stored in the data block that follows this header. It can either be a basic program, a basic array, or a block of binary code. We will look at basic programs and code blocks a bit more in detail later. Other information contained in the header are an optional name, the size of the following data block minus the 2 bytes of tab block length, and finally the block parameters that further describe what to do with the following block. Now let's look at the data block. Here the flag bytes value is always FF hexadecimal or 255 decimal. The checksum byte is computed in the same way as in the header, by applying XOR on the bytes that come before it. If the header indicates a program, there will usually be basic code stored here. If the type is code, the data can be any type of binary information, and arrays are basic array variables that were stored on tape, which can be either text or numbers. We will see how numbers are stored when we take a closer look at basic programs. When I talk about a block in this video, I often mean a header block in combination with its corresponding data block. Even though these are stored in two separate tab blocks, they really should be viewed together. I mentioned earlier that headers contain block type specific parameters. Here are the parameters for a program block. The second parameter is typically equal to the size of the data length that we have already seen in the header. The first parameter is the auto-start line. It tells the load function which line to start the basic program from. From the Spectrum Basic interpreter, this value can be defined with the save command. If the line was not given in the save command, that value is 32,768 and the program will not be started automatically. I should mention that on the Spectrum Next Basic, programs will generally be stored in +3 DOS files on the SD card rather than tab files. These are files with a special 128-byte header with a different structure, but the information contained is very similar. These are the parameters for a code block. There is actually only a single parameter, which is the start address at which the data should be placed. Since BASIC doubles as the command line interface on the Spectrum, it is useful to have some knowledge of the language, even if you plan on programming in other languages. Basic programs on the ZX Spectrum are essentially stored as a series of tokenized lines, and Next Basic has adopted the same structure with an enhanced token set. I am deliberately leaving out a couple of the finer details for special cases, because I won't need them for my purposes at the moment. As you can see, it starts with a 2-byte line number, which curiously is in big endian, followed by the number of bytes that follow in that line, encoded in little endian format as is the standard on the Z80. Following that is the tokenized basic code for that line, and finally the line ends with an end-of-line character. Basic tokens broadly fall in 3 general categories. First, basic keywords, which translate to a 1-byte number. Numbers such as integers and floating point numbers that have a special representation, and general characters such as strings and delimiters, which are represented by their ASCII code equivalents. This is how numbers are encoded within tokenized basic lines. For integers, it starts with the characters for the string representation, followed by the number marker hexadecimal E0. Then comes a 0 byte, then a byte for the sign, which is FF for negative numbers, the integer number itself as 2 bytes in little endian format, and finally a 0 byte. A floating point number starts with the string representation and the E0 number marker, and then 5 bytes for the binary representation, where the first byte represents the exponent, and the last 4 bytes represent the mantissa in base 2, encoded in big endian format. So now that we gained all that knowledge about the structure of tab files and basic programs, how can we put this to good use? For one, it helps us to understand how tools work that manipulate tab files in order to use them more effectively. Or we could just write our own tools. One important application is to have our programs that were written in assembly code or a compiled language automatically started after they are loaded, and maybe even include a splash screen. We could also write our basic programs using our favorite text editor on the PC and use a tokenizer to create a program that can be read on the Spectrum or Spectrum Next. I will be showing a few examples in a moment. I have written a couple of command line tools that I will use for the following demonstration. You are welcome to check them out or use them as a reference. The easiest way for most people would be to install them through pip. The source code is available on GitHub, If you work on Windows, you might want to either use Windows Subsystem for Linux or alternatively Cygwin or MinGW if you are more comfortable with that. I will be using the game Sanction for most of the demonstration. That's mainly because it is on the Spectrum Next SD card and because it follows all the rules that I just mentioned. For convenience, I will be using Fuse as the emulator for this classic ZX Spectrum and Cesar Urex for emulating the Spectrum Next. Let's start a game. You see a splash screen, and when you hit a key, you are in the game right away. So what does this mean? I would expect that there are at least 3 blocks in the game's tab file. A basic loader program, a splash screen block, and finally the machine code for the game itself. Let's see how the tab file is structured. As expected, we are seeing 3 header data block combinations. The first is a relatively short program block. This is the basic loader. The second is a code block of 6912 bytes, then has a start address of hex 4000 or 16,384 decimal. Whenever you see a code block of 6912 bytes at address hex 4000, it is typically a splash screen. The third block is another code block that is 22,303 bytes long and loaded at address hex 6800 or 26,624 decimal. This is the game's machine code. Let's take a peek at the basic loader. There are a couple of basic instructions that mostly affect screen colors and load messages. The important part are the 2 load commands, which load the 2 subsequent blocks for the splash screen and the machine code. Then there is the clear command, which makes the memory available for program code starting at address 24,576. And finally, the randomize user 26,624 command invokes the machine code program that was loaded at that address in memory. Let me show you how tab files that consist of multiple blocks can be split into their individual units. We know that the second block, that would be the one numbered 001 in the split files, is a splash screen. Since that block already contains the correct start address, the Spectrum can load and display that splash screen right away. Okay, I will now demonstrate how we could possibly type in basic programs on the PC and generate tab or BAS files to run them on the Spectrum or Spectrum Next. To be honest, BASIC is one of those languages that feel more natural when working directly on the machine. But for creating basic loaders, it should be just fine. First, I will type in a basic program for the classic Spectrum. This is just a simple Hello World program. Now I will use my utility BAS to tab to create an auto-starting tab file. When I double-click on the hello.tab file that was generated, the emulator automatically loads and runs the file. I can use the same tool to create a BAS file in +3 DOS format to run on the Spectrum Next. Let's type in a basic program that only works on the Spectrum Next. I am using the format switch to specify that I want to create a +3DOS file. Now let's load the program into the Spectrum Next emulator. Alright, that was a look at the tab format. I wanted to look at something that was going to be useful for a variety of things, especially for writing games and the compiler that I'm currently working on. Using tab files allows me to stay compatible with the older and more bare bones machines while still being able to take advantage of the Spectrum Next improvements. When it comes to the Spectrum, I am essentially starting from zero, and understanding the tab format is only the beginning of the journey into ZX Spectrum and Spectrum Next development. My goal is to write programs and games that run on both the Amiga and the Spectrum Next, and then I have a couple of ideas that I want to try out, and I will try to document my progress and experiences along the way. Thanks for stopping by. Until next time.